Well, hey there again, Bio30s. Here we go. So, this is going to be a very important lesson for you today. One of the most difficult concepts in Bio30 to understand is how signals are transmitted through the axon, right? And by neurons to other neurons will be done in another lesson. So, we're going to split this into two lessons here. Today, we'll be looking at electrical transmission. And then in the next lesson, we'll be looking at chemical transmission. Let's get this pointer going. Cuckoo. All right. You need to review these. All right. So you need to review your facilitated diffusion and your, what's it called? Active transport. There we go. This is a specific type of active transport with the sodium-potassium pump. And this is the one we'll be looking at today. So it's 2-in-1 for you. All right. Also with these voltage-gated ion channels, this is a type of facilitated diffusion. Please take a look at these videos before you continue so that you understand more of the lesson. All right, so I'll let you do that. You'll need Adobe Flash Player active on your computer in order to run a lot of the animations that I've posted for this lesson. So like I said, we'll be looking at electrical transmission today. And electrical transmission what we call an action potential, all right? And this is an electrical signal. It starts in the soma and it runs through the axon to the axon terminals, where then what will happen is that chemicals will be released from the axon terminal. So here's an axon terminal, all right, and here's a dendrite on this side here, and then chemicals will be sent across, right? So we have electrical signals called action potentials reaching the terminal, where chemicals will be released and sent to the next axon, and this would be the soma of the next axon here. So we're going to explain to you how that happens. Okay, so we need to understand first of all that axons have voltage. You're like, what do you mean they have voltage? Well, if we're going to send electrical signals, we need voltages set up. Okay, so what we need to understand here is that outside the axon, we have overall positive charge. Inside the axon, we have overall negative charge. And the positive charges on the outside of the axon are caused by an accumulation of sodium ions. And this is the most important ion for you to understand in electrical transmission, is that the sodium ions, all right, are the ones that cause this voltage. And at a certain point, sodium ions are going to start to rush in to the axon, all right? And this is what we know as the action potential. Now I'll explain why they rush in as we go through this. But what I want you to understand first is as they rush in, all right, they allow more sodium to rush in front of them, all right? And again, I'll explain this as we go along. So you can see in this picture here, sodium rushes in, it causes more sodium to rush in, it causes more sodium to rush in, it causes more, and you can see how that action potential, that electrical signal, moves down the axon. Now, you're seeing here like, wait, what's this potassium business, right? We have potassium ions here too. What are they for? Okay, and I will explain that to you as we move through. But we want to, first of all, just understand that the sodium rushing in, all right, to the axon will create a voltage change. And you can see how the voltage has changed from negative on the inside to positive on the inside when the sodium rushes in. And so this red piece here is an action potential, all right? It is an electrical signal. So how does this all work? Okay, I'm going to stop this. You can go and read this on your own. There's a good video linked in here for you, as well as an animation linked in here. All right, this video linked here is pretty long. It's a very good video. you should watch it probably after we do this lesson um, together. So here you see I have your workbook page identified here, and I'm going to move to the next slide here so I can, oops, there we go, compare these two. I'm going to help you fill out your workbook here because this is one of the, I usually draw this whole thing out on the board. So here we go, all right? So label, this is a sodium channel. This is a potassium channel. This is a sodium potassium pump. So these are both gated ion channels, and this is a sodium potassium pump here. So in the resting potential, what we have is an accumulation of sodium ions on the outside of the axon. So you want to start drawing these in. Draw a bunch of sodium ions in here. An accumulation of potassium ions on the inside of the axon. Okay. Now, they're both positively charged ions, and we have to understand that even though they're both positively charged ions, we're going to have a membrane potential set up here, and I'll explain how that works. So on the inside here is a negative 70, and this is what the resting potential is negative 70. So right here on the graph, we have a negative 70. So you want to, again, identify that negative 70 on your graph here as well, all right, and highlight this portion of the graph because this is what we're talking about here. This is the resting potential or the resting membrane. Okay, now why do we have a voltage across the membrane? Why is it more negative inside and more positive outside? And this is a very simple answer. There's more positive ions on the outside, and those are represented by sodium. Okay, so there's more positive than negative ions on the outside. There's accumulation of positive ions. Now, potassium is in a high concentration on the inside, all right, relative to itself on the outside. However, okay, there's more negatively charged ions in the inside, things like hydroxides and especially chloride ions. Okay, they accumulate inside, and so there's more negative charges inside. So again, make sure you understand that sodium is accumulated outside, and it has a what do we call that? I'll get to it, right? So it can diffuse inside, so it has a diffusion gradient. There we go, all right? It has a gradient. High sodium outside, low sodium inside. High potassium inside, low potassium outside. So you want to draw these in, right? So you know in any way that makes sense to you. Okay? And there's more positive charge outside in total, and there's more negative charge inside in total. And that's the way we should understand this. If that's unclear to you, please rewind the video now and re-watch it, okay? Because you'll need to understand this point. Okay, so resting potential. We have a potential for an action, potential to arise. So we're going to go to the next step, which is depolarization to the threshold level, all right? So what is this threshold level? First of all, the threshold level is around negative 50, negative 55 millivolts. And you see here the threshold level is identified in the graph here. So you also want to identify a threshold level in your graph, and you want to, again, just like you did here in negative 70, you want to put a negative 55 in here. Now, what happens is that a stimulus, any stimulus, all right, opens the gates on the sodium channel. So here the sodium channel's open. So what happens is that sodium moves down its concentration gradient. So draw this in, an arrow with sodium moving down the concentration gradient, all right? And so now it depends on how strong the signal is and how many sodium channels, all right, get opened, okay? If not a lot of those sodium channels get opened, then what happens is that, all right, okay, let's back up. As sodium channels get opened, what happens to the voltage inside? It starts to get higher. So the negative 70 starts to increase as sodium rushes in, okay? Now, If it does not increase to negative 55, if the stimulus is weak, it's going to fail. You're going to have a failed action potential, meaning that that stimulus will not be recorded. All right, you will not actually feel that stimulus as something. Okay, so it will not. So there's lots of stimuluses coming at you that you're actually not perceiving, you're not feeling them because they don't reach threshold level. Okay, so this is what this means: is the depolarization is the rushing in of sodium. So this whole line is actually depolarization, but we're only concerned with this. So what I want you to do here is draw in where you have your threshold level, draw in a little blip here, all right? Just a little line going up and down, meaning that actually, so, and label it, all right? Is that if the stimulus is not um, strong enough, it will not create an action potential and it'll just go back to the resting potential. Okay,